Welcome everyone. We are pleased to present our project work titled Design and Simulate a Hybrid Power System for Hopedale Labrador. This work was completed under the guidance of Professor M. Tariq Iqbal at Memorial University. In this presentation, we'll walk you through the motivation, method, and outcomes of our hybrid renewable energy system adapted for a northern off-grid community. Here's a brief overview of our presentation. We'll begin with an introduction outlining the need for hybrid system in that remote area. Next, we'll highlight key points from our literature review. Then we'll go through our methodology, including site analysis, load profile, and meteorological data. Finally, we'll present our system design and sizing results using Homer Pro and conclude with the major outcomes of our study. Hopedale is a remote Labrador community that relies heavily on diesel generator for power, which comes with challenges like high cost, difficult fuel transport, and environmental impact. To address this, we are proposing a hybrid system using solar PV, wind turbines, and battery storage to increase reliability and reduce dependence on diesel. We used Homerproof for steady-state system sizing and MATLAB Simulink for dynamic performance analysis, aiming for a cleaner, most cost-effective solution for Hopedale. The shift to renewable energy is driven by the need to limit global warming to 1.5 degrees Celsius, as outlined in the Paris Agreement. Effective strategies including electrifying transport, improving energy efficiency, and integrating carbon capture. Microgrids are particularly useful in remote areas like Hopedale as they combine renewable and energy storage systems, offering both reliability and flexibility. In Newfoundland, wind energy has shown more promises than solar due to the region's low solar irradiance. Tools like Homer Pro help evaluate such hybrid systems for performance and cost efficiency. Technically, hybrid system combines PFE, wind, diesel, and batteries to ensure stable performance. Simulation tools like MATLAB Simulink help to create a system dynamic model in real time. Advanced MPPT method using perturb and observe combined with fuzzy logic improve energy capture from PV and wind. In Arctic region, intelligent control systems have been developed to reduce diesel usage and protect wind turbines from icing. Such automation enables high renewable energy penetration and operational resilience, which is exactly what remote communities need. Now, our approach combines data collection, modeling, and simulation. We started with a detailed site analysis of Hopedale to understand its constraints and resources. We analyzed load data, then collect solar and wind data to understand seasonal trend. Using this, we performed simulation in Homer Pro to identify the most economical system configuration followed by MATLAB simulation to study dynamic behavior. Now, Hopedale is a remote coastal town in northern Labrador with about 596 residents. Year-round, it has no road access and depends on a diesel-based power system, which is expensive and polluting. Because of its latitude and exposure to wind, the site has a strong potential for both solar and wind energy. This factor make it an ideal candidate for a hybrid renewable energy system. Community's energy demand shows a clear seasonal variation. The highest demand is in January, about 15,500 kWh per day due to heating loads. The lowest demand occurs in August, around 9,000 kWh per day. Understanding this pattern was key to determine system size and storage requirements, ensuring we could meet demand throughout the year. From our data, Hopedale received an average solar irradiance of 2.83 kWh per meter square per day and an average wind speed of 7.98 meter per second. While solar generation is limited during winter, wind speed remains strong year-round, making wind turbine highly effective. Combining both sources allow us to balance seasonal generation with solar in summer and wind in winter. The use of diesel as backup ensures reliability when renewable output is low. We used Homer Pro to design an optimal system combining PV panel, wind turbine, diesel generators, and battery storage. This hybrid configuration maximizes renewable penetration while maintaining reliability and cost effectiveness. The schematic includes a DC bus system, inverters, and charge controller integrated with energy management strategies. Our final system includes the following components: PVRF 1924 kilowatt, 9 units of wind turbine is 95 kilowatt, will retain the existing 910 kilowatt diesel generator of that community, 4,820 units of battery bank for storage, 1800 kilowatt of converter capacity. This configuration showed the lowest net present cost, lowest emission, and high energy reliability in our simulation. Now, I am welcoming Priyanto to carry out the next section of the presentation.
So in this part of this project, we use Homer Pro optimization software to optimize the overall system and to see which system is best suited for us. So after all the analysis, Homer displayed us the best suited system that is actually best for us for this location, Hopedale, Labrador, and we can see that the system actually generate uh, 700,000 almost 700,000 kilowatt hour electricity per year. So out of that, wind turbine provide 64% of the total generated electricity, whereas solar PV contributes 32.9%, and diesel generator serves as a backup, providing 3.1% of the generated electricity. And in this system, there is an excess electricity of 24.9%, but as there is a seasonal fluctuation of the load in that area, so this excess electricity will be utilized. The proposed hybrid system reduces diesel consumption to 65,122 liters annually, averaging 178 liters per day. This results in a 95% decrease in diesel-related emissions compared to the current system. Fuel usage is minimal and consistent throughout the year, indicating effective renewable integration. Here we can see the proposed system significantly reduces the net present cost from 41.36 million to only 16 million, saving over 33 million in diesel fuel cost. Major capital costs included wind turbine, PV, batteries, and converter. Cost breakdown shows wind as the largest investment, followed by battery storage and solar components. So emission plays a significant part when designing this system, because in order to achieve the 2050's net zero emission goal of Canada, so we need to build a system that actually emit less toxicated gases. So the proposed hybrid system achieving significant emission reduction, including 95% less carbon dioxide and 99% less CO and unburned hydrocarbons. Other pollutants like SO2, sulfur dioxide, particulate matter, and nitrogen dioxide also see reduction of 94 to 95%. This highlights a hybrid system's strong environmental performance compared to a diesel-only setup. So we also used MATLAB Simulink to see how our model actually demonstrate how our model actually works when we actually build the system in real life. So that dynamic model includes MPPT control PV array, wind turbine, diesel generator, battery, load models, and this parameter matched with Homer. As we can see, these are the results from our input from wind turbine. So here in the slide is from wind turbine output and solar PV output. So we can see that the wind turbine output stabilizes around 80 kilowatt, showing smooth and consistent performance. The solar PV output reaches up to 400 kilowatt, with current rising potentially to irradiance level. Both systems demonstrate effective energy generated aligned with environmental conditions. So this slide consists of diesel generator output and load power curve. So we can see that the diesel generator delivers stable output at 400 volt and 2000 kilowatt, supporting system load during demand peaks. Load current reaches around 1000 ampere with power around 540 kilowatt, indicating efficient energy delivery. So, and also this system has a lower total harmonic distortion, which is THD, confirms the system produces clean and renewable energy. Uh, so this is the result from the battery management analysis. So the battery current and power peak early, then stabilize, reflecting a transient load followed by steady demand. Voltage remains steady around 48.7 volt, confirming reliable battery operation under load conditions. Control strategy is very important for a hybrid power system. So we designed a control system that will ensure reliable power for that community. The system employs a combination of on and off PI controller and also PID controllers to ensure stable and efficient operation. It regulates the power flow, maintains battery health, and optimizes energy utilization. So we also use a charge controller here, as we can see. It is a PI-based charge controller, which dynamically adjusts the charging current based on state of charge and load demand. And the PI controller, as we can see, the logical control block diagram enables seamless switching between renewable sources and the diesel generator. We have also used a control strategy for our load side and also use the PWM controller-based buck-boost DC-DC converter. The system adjusts power flow automatically based on changes in load demand using the relays. A protection mechanism isolates component during overvoltage or overcurrent fault. The DC-DC converter regulates voltage for battery charging, maximum power point tracking, and load stabilization. A PID control pulse width modulation dynamically adjusts the duty cycle to ensure stable voltage and optimal power transfer. So in conclusion, we can say that we have key points, we have found the key points so that we can say that this hybrid system is very efficient in terms in compared with that conventional diesel-based system. So first of all, addressing high diesel dependence. Our project targets the costly and emission-heavy reliance on diesel power in remote communities like Hopedale and Labrador. Sustainable hybrid solution. We offer a reliable, eco-friendly alternative by integrating wind and solar with diesel backup. Economic benefits. Reduced fuel cost and lower operational expenses mean long-term financial saving for remote communities. And also, this model can be adapted to similar isolated regions worldwide, supporting clean energy adoption on a global scale. And lastly, as we know that Canada has a net zero goals that within that's the year is 2050. So this hybrid system aligns with Canada's 2050 net zero goals, contributing to a cleaner environment and reduced CO2 emission. And I hope everyone have liked our presentation and have a good day.